Hello everyone, what's up? Welcome you all to this channel. I'm Shiraz Ahmed and here is a brief profile about me. So my friends, today we'll start chapter number 4 and in this chapter we'll cover concept related to buoyancy and floating. So the topics that will be covered in this chapter are buoyancy, like what buoyancy is. We'll also study the principle of flotation and also we'll see the equilibrium condition of a completely submerged body and a partially submerged body. So what are the various conditions for these bodies to be in equilibrium? We'll also discuss about metacenter concept, and in the last we'll study the fluid in relative motion. So let us start with our first topic, that is buoyancy. What is buoyancy? So as we can see in the picture, we are having two bodies. One is floating and another is sinking. Okay. So buoyancy is about like a force. Buoyancy is nothing but it is upward hydrostatic force. Okay. Definition you can read here. So when a body is immersed completely or partially, then it will experience a upward force. Upward hydrostatic force. Very important. Okay. Don't forget this term, which is known as a buoyancy force. So basically how this upward force will come. So let's suppose we are talking about the fluid particles here, okay? And here it will be certain pressure, right? And it will be normal to the body surface, okay? So like this, normal. So if I'll take the component of these forces, one will be horizontal and one will be vertical. Similarly, opposite to this point, we are having this point, right? So here also one horizontal and one vertical. As they are in horizontal position, the pressure remains same. So this horizontal point, right? These horizontal forces will get cancelled with each other. So how the pressure will be same at horizontal line, we have studied in previous concept, okay? So now will be remaining with the vertical force only. Similarly in this case also, normal force, and we can take a component here this way, and same on the horizontal point will be having the same pressure. It will create the same amount of force in this direction, horizontal and vertical. Horizontal will get cancelled with each other and will remain with the only vertical force. And when we sum these forces, there will be net vertical force in upward direction, that will call as a buoyancy force. Similar to this point here, right? Here if we'll talk about similar to like just vertically upward, it will also experience same way, right? These forces. So horizontal will get to cancel each other. So this, let's suppose we call F1 and here it is F1 dash. So F1 will reduce the impact of F1 dash. So net vertical force will be F1 dash minus F1. So this is to understand basically the concept. I'm explaining this to understand the concept. So why there will be upward? Because this F1 is caused by pressure here, right? P1. And here F1 dash will be caused by pressure P1 dash. And as we can see, it's vertically downward P1 dash. So P1 dash will be more than P1. Or if I'll say the exact relation, it will be P1 plus density of the fluid G into delta H, the distance, vertical distance between these 2 points. So this concept we have studied earlier and we are using now, okay? In chapter 1 and 2, this concept has been studied. If you want to have a clarity, you can go and watch those chapters as well. So now buoyancy concept is clear, and what is buoyant force is also clear. So the resultant of these vertical forces F1 dash and F1, there will be multiple points, then F1 to Fn and then F1 dash to Fn dash. So if I'll resolve all these components, then I'll get a vertical force that will be called as a buoyant force. So let us consider one more example here. very confusing example. So see, try to like understand the essence what exactly the buoyancy force. So this is the case. I am having a fluid of density rho. This is the free surface, and I am having one body here lying in this direction. Okay, and there will be fluid all top of it, and then having same body that is only reversed by 180 degrees. Same body. Okay. So now the question is very simple here. Body 1 and body 2, they are same, but just convention is opposite, right? So 180 degree rotated upward. So question is, does 1 and 2 both, this is the question, does 1 and 2 both will experience buoyant force? So you can stop the video for a moment, try to think, and then we will see. Okay, so now, so hope you have all come up with your solution. So let us try to understand this concept. So as we can see, a fluid particle will be here, right, on the top of this. So it will be experience pressure in this direction, right, normal to this surface. If I'll resolve this, so I'll be having a force in this direction and force in this direction, right? Similarity to with these points. And just opposite to this, I have taken one more point. It will also experience a force in horizontal and vertical direction. Okay. Will there be any force from here by the fluid? It will be, yes, there will be force, but it will be by the this surface, fixed surface. It will not by because of the fluid. So this horizontal force will be cancelled with each other, and then we'll be having a net downward force, F net, right? And this downward force will be balanced by the force provided by the surface. So fluid will not apply any upward hydrostatic force. So buoyancy force will be zero in this case. Try to understand the definition. Upward hydrostatic force. So what is buoyancy? What you will remember here, it is upward, three keywords, hydrostatic and force. So these three keywords only you have to memorize. What is buoyancy? Buoyancy is upward hydrostatic force, right? Body is floating or sinking. So let us now understand the body number 2. So these will be the fluid particles, right? It will experience force here in this direction, right? And then similarly opposite to this, it will experience horizontal force and vertical force. This horizontal force will be cancelled with each other, right? And then at this point we'll be having this only F1 forces. Okay, and if we'll go at the top of this surface, there is just just vertically up, then this will also experience some force. Let's call it the F1 dash. So as it is vertically up, so pressure here will be lesser, right? Pressure here will be lesser. So there will be net vertical force F1 minus F1 dash in upward direction, and this will be called as a buoyant force. So here we'll be having some buoyant force. So now let us try to calculate the numerical value of this buoyancy force. Now, like how we will evaluate this buoyancy force numerically. So for that, let us consider a fluid of density rho. So this is a free surface and a cylinder is floating. Right. So this is rho f is the density of the fluid, and rho s is the density of this solid block, cylinder block. Okay. So this will be the center of gravity. Okay. height of the cylinder is h. Okay, so now I'll draw the FBD, force body diagram. It's very simple. So these surfaces will be experience normal force, same here, and they will cancel with each other. This surface will experience certain pressure from the downward, and this point will experience force from here, and this will be PATM, atmospheric pressure, and here some pressure will be there, right? And let us consider it is floating with depth of float is h. So it is floating in a deep water, like at a height h. So what will be the pressure now here? P PATM plus rho fluid G into H. Okay. So now I'll make the FBD, right? And it will also experience weight of the cylinder. So due to the hydrostatic, how much net upward force this cylinder is experiencing? So F upward P into cross-sectional area minus PATM into cross-sectional area. So this is nothing but P minus so what is P minus PATM? From here it is nothing but rho F GH into A. What is H into A? This volume, right? It is nothing but the displaced volume of fluid. And this F upward is nothing but the buoyancy force. So this is the numerical formula for buoyancy force. It is nothing but the weight of the displaced fluid. What is this expression? Weight of the displaced fluid. Okay. So now let us move to our next concept, that is principle of flotation. So what it says, in equilibrium of submerged body, partially or completely, the weight of the body is equal to the buoyant force, that is weight of the fluid displaced. So if the submerged body is in equilibrium, for example in the previous case that we have studied, so if it is in equilibrium, it means whatever the net upward force, what was it? Was buoyancy force, that is FB, right? And this buoyancy force will balance the weight. This is what the law of flotation or Archimedes principle. And this buoyancy force, buoyant force, acts upward through the centroid of the displaced volume. So for example, if I consider a cylinder which is floating, right? This is the free surface, and this will be the G. Okay, so whatever the displaced volume, right? This will be the displaced volume. So its centroid will be the buoyancy force, right? So somewhere here, center of buoyancy. So whatever the centroid force will be, like from where the buoyancy force will be there, like it will be the centroid of the displaced volume. So this is what about the principle of flotation. So now we'll talk about the equilibrium conditions, right? For example, what are the various equilibrium conditions? Let us try to understand. It is a 12th concept, so we are going to revise. We are not going to learn anything new. Okay. So if this is a ball and if I displace it from its mean position to some other position, right? So it will naturally it will try to come to mean position, right? Naturally by its own. You don't have to do anything else. So this will be called as a stable equilibrium. So if something comes to their equilibrium position automatically, then it will be called as a stable equilibrium. Okay. And if it does not, then there are two cases. So now we are having this ball and is in mean position right now, and I displace it from its mean position, right? So it will go to its next position here, right? And it will remain at this position for as long as you don't apply an external force again. So this is called as a neutral equilibrium. Next condition is this. This is a mean position. If I displace it, right, and remove the force, then it continue to move in the opposite direction, like away from the mean position. So it will be in unstable state. That is called as unstable equilibrium. So now we are going to use these concepts to learn the equilibrium condition for completely submerged body and partially submerged body. So let us consider the first statement, that is completely submerged body. This is a fluid. I'm having a cylinder of cross section area A. It is completely submerged. Okay. Now let's suppose center of gravity is here for this. It's in non-uniformly distributed. Okay. And the displaced volume of the fluid will be this, right? What is the centroid of that volume? This is the centroid and this is the buoyancy. Center of buoyancy, right? Now I'll draw the FBD, weight of the block, and then the buoyancy force, right? So let us consider what are these two parameters. W equal to density of the block into V. What is FB? Density of fluid G into displaced volume of the fluid is nothing but V only, right? Because it is completely submerged case. So now if I'll try to turn this, let's suppose what I'm doing, I'm trying to turn this block. Okay. Let's suppose I have turned like this. Okay. So G will be here and buoyancy will be here. Right? W, G, and this force will apply in this direction. Let's suppose I have given a small deflection, right? Okay. So now I'll evaluate the moment due to this buoyancy force about center of gravity. Moment about CG due to buoyancy force, right? So I'll extend this. I'll make a perpendicular from here. Let's suppose this is R. Okay. So this is nothing but FB into R. What will be the direction? It will be in the counterclockwise. Counterclockwise. Right? So I try to move this into the clockwise direction from its equilibrium position. Okay. And what will be the effect of the buoyancy force now? It will try to move it towards the mean position, right? Because when I have moved in this direction clockwise, the moment applied by the buoyancy force is counterclockwise, hence it will try to return to its previous position, hence it is stable equilibrium. Okay, so in case of fully submerged body, fully what we studied? We studied that when center of buoyancy is above CG, then it is stable condition. Similarly, let's suppose if it is not above it, if it is below, let us consider that situation. It is fully submerged. I am having CG here and buoyancy here. Let's suppose, okay, and I again turn this by a small angle. Buoyancy will be in here and center of gravity will be here, right? W, G, and FB. So I have moved in the clockwise direction. This one into clockwise direction. So if I'll calculate the moment, or if I'll see the moment about CG due to FB into R, and it will try to move in the clockwise direction only, right? The sense will be clockwise. So it is trying to move the body away from its mean position. Then it will be unstable equilibrium, right? If we'll try to understand in this fashion, then it will be not very difficult to understand the concept. So when it is unstable, when COB, center of buoyancy, is below CG, then unstable. Similarly, if we'll try to understand, then when it will be neutral equilibrium, when COB is at CG, then neutral equilibrium. Similarly, you can perform this exercise by yourself, and if you have any doubt, you can come back to me. Okay, so this is all for the completely submerged body. Now we'll move to partially submerged body. Try to understand. Okay, so what is first? Let us see what is the partially submerged body. This is the water, free surface. I'm having cylinder. So this is a partially submerged body. Okay. Then I am having G here and buoyancy force here. Okay. So in this case, only buoyancy and center of buoyancy and center of gravity will not help us to determine the equilibrium condition. For this, we have to learn one more concept that is called as a meta center. Okay. So let us try to understand what is meta center. So for understanding this concept, again I am redrawing the same thing. Partially submerged body. Okay, this is the axis. Okay, and this is the CG, let's suppose, and this is the buoyancy, center of buoyancy. So what I have done, now what I'll do, I will turn the same thing by certain degree. Okay, same cylinder, I have turned it. Okay, this is that line. This will be the G again, center of gravity, and let's suppose this is B, that is older buoyancy. Now the center of, like, centroid of this displaced volume will be shifted and it will be somewhere here, B dash. And if I draw a vertical line from here, it will cut this axis somewhere, right? Joining G and B. It will be called as a meta center. Okay. And buoyancy force will act in this direction, FB dash, new buoyancy force. So if I have rotated this in this direction, right? Okay, because see, because it is a partially submerged body. So center of, what is the difference between fully and partially submerged body? Now we have to try to understand the difference between these two. Just now we have studied fully submerged body, and now we are studying partially submerged body. So what is the difference between these two? Is that in this case the center of buoyancy after rotation will change. That is the one big difference between these two cases. And you try to write this concept, it's very important. What? Center of buoyancy changes after rotation in case of partially submerged body. So when I draw a vertical line and it cuts the previous older center of gravity and buoyancy joining 2 points, that line, then it will be called as a meta center. And meta center will be collinear with older, like with center of gravity and older buoyancy. Okay. So now let us try to understand whether this is a stable condition or not. So what I did, I have tried to rotate in this direction. What will be this new buoyancy force tendency of rotating this block? Where will be the tendency about G? So if I'll try to calculate the mg, is nothing but fb dash into a, and sense will be counterclockwise. So it will try to rotate this block into its mean position, towards its mean position. Okay, hence it is stable equilibrium. Okay, when it won't be able to, what will be the case when it is unstable equilibrium? Let us try to understand that from the same figure. No, we'll draw another figure. Let's suppose this is the rotated thing. Okay, and having G here and buoyancy here, and B dash comes here, right? So if I'll draw vertical line, M will be here, right? So what will be the now direction of this moment? It will be clockwise. So it will move this block away from its neutral position. Hence it is unstable equilibrium, right? So what are the conditions? Let us try to write down the condition. When it is stable and unstable? Partially submerged body will be stable when M is above G, unstable when M is below G, and neutral when M is coincides with G. Okay, so hope till now the concepts are clear to you all. So let us try to evaluate these values like Gm and the distance between center of gravity and meta center height, that is Gm, right? So let us try to understand those things. Again, I am considering the same condition. This is G, this is B, and I am having M somewhere here, stable condition. Okay. So what is GM? GM is called as a metacentric height. And it can be evaluated by, what is GM here? From this diagram we can see BM plus BG, right? What is BM? BM is metacentric radius, and it is defined as a I upon V. What is V? V is the displaced fluid volume, and I, so for considering the stability, we'll take the minimum I. What is I? I is nothing but, if I'll talk about the surface, right? So there will be two area moment of inertia. One is about this axis, right? One about this axis. So it can rotate either in this direction about this axis or about this direction, right? So whichever is the minimum I value, right, that will be the most critical condition, right? Because there the BM value will be smallest. Okay, smallest means closer to B. So it may become instability. For example, let us consider this one more condition here. Let's suppose it is G and this is B. So the now formula modifies to GM equals to BM minus BG, right? So when I reduces, right, so the metacentric BM will reduce and it will come closer to GG. And when it becomes below G, then moment it becomes below G, then it is unstable. So the most critical condition is where the moment of inertia, about which axis the moment of inertia is minimum. Okay. For example, if I consider a ship, this is a, let's suppose this is a ship. Okay. So it can do two motions, right? One is rotate about this axis, that is roll, and then rotate about this axis, that is pitch. So which one is minimum? I roll is minimum, right? I roll is less than I pitch. So whenever we talk about the stability, we'll calculate the BM corresponding to I roll and GM correspond. Then GM will be calculated corresponding to roll only. BM roll minus BG, that is I roll upon VF minus BG, right? And if this GM is positive, right, then GM pitch will also be positive, right? Why? Because GM pitch is always greater than GM roll. Okay. Why is it so? Now question is, why is it so? Because I pitch is greater than I roll. Simple. Okay, my friends. So I hope this concept, like numerically how to resolve whether certain ship is stable or unstable. So we'll evaluate GM basically. If GM is positive, then stable, like M is above G. And if from this formula, if GM comes 0, then neutral. and if gm becomes less than 0, then it is unstable case. So this is another criterion based upon the gm. Okay. Now we will study this time period of oscillation. What it is? T equals to 2 pi square root of k square upon g into gm. So for ship case, there will be two time period of oscillation, right? One is about roll and one is pitch. So respective we'll put gm values. Okay. What is gm? Gm is nothing but metacentric height. So respective gm value we have to put either pitch if we want to find the time period of oscillation about the pitch, then we'll put gm pitch value. Okay. And what is k? K is nothing but radius of gyration. What it is? Square root of I upon a. I is the area moment of inertia for that rotation, either pitch or roll, and a is the corresponding area, the surface area. Okay. So this is the way to calculate the time period of oscillation for this case. Okay. So let us conclude this lecture now, my friends. This fluid in relative motion will cover in part 2 of chapter number 4. In case of any doubt, you can ask in the comment section of this video. For more videos and regular updates, subscribe to this channel. Thank you all for watching this video.